Hi everybody. Our next topic that we're going to work with, we're going to take a look at another method for solving quadratic equations. We're going to develop and use the quadratic formula, and then we're going to explore the quadratic formula by working with a part of the quadratic formula called the discriminant. So let's get started. Let's begin by doing just a little bit of review. Take a minute, pause the video, and see if you can, I hope you can, from our work that we just completed, see if you can solve this quadratic equation for x. Pause the video and then resume when you're ready to see the solution. Don't just let it play and follow along. Make sure that you stop the video and do this so that you can practice the skill. It's tempting to just watch, but stop and do it. Okay, let's take a look. You might remember that our first step is to get the x terms together on one side of the equation. So I'm going to add x to both sides here. And so we end up with 3x squared plus x minus 10 equals 0. Now that 3, the leading coefficient of 3, has to disappear here. We need that to become a 1. So let's divide both sides by 3. And we have a new quadratic that is x squared plus 1/3 x minus 10 over 3 equals 0. Now our next goal is to get this spot cleared up right here. We need that opened up, so we're going to add 10/3 to both sides. I'm not going to show that step. X squared plus 1/3 x is equal to positive 10/3. Now we need to complete the square by putting in the number that we want right there. Since our b value is equal to 1/3, then half of our b value, or b divided by 2, is going to be 1/3 times half, which is 1/6. So we're going to add 1/6 squared to both sides. Now on the left side from our work in the previous topic, we know that that is going to factor to become x plus 1/6 squared. And on the right side, that's going to become 10/3 plus 1/6 squared, which is 1/36. Now again, avoid using decimals there. In fact, don't just avoid it, don't do it. We're going to do all of our work using fractions here. If we put these two together on the right side, our common denominator is 36, and that's going to be 120 over 36 because we're going to multiply top and bottom by 12 here to get our common denominator, plus 1/36. And so that means that our quadratic is now x plus 1/6 squared equals 121/36. Now we can take the square root of both sides. And when we do that, we get x plus 1/6 is equal to plus or minus 11/6. So let's subtract 1/6 from both sides, and x will be equal to negative 1/6 plus or minus 11/6. Okay, now if we evaluate each of those, negative 1/6 minus negative 11/6, we would have x equals negative 12/6, which reduces to be negative 2. There's one of our two solutions. If we add, we would get x equals negative 1 plus 11, that's 10/6, which reduces to become 5/3, and there's our other solution. So our quadratic yields two solutions here. Looking forward into our topic for today, we would have been able to tell that we were going to get two solutions and that they'd be real way back here when we had our initial quadratic, and we're going to see at the end of our topic today why that is. Okay, let's steal this idea and let's solve a general quadratic where a, b, and c are any real number. We'll start, of course, with ax squared plus bx, but now let's add that subtract c from both sides to open up the space we need. Now let's divide both sides by a, and that gives us x squared plus b over ax equals negative c over a. Now we're ready to fill in the number that we need. Our coefficient on b here is b over a. If we take b over a and take half of that, we get b over 2a. So we're going to add b over 2a squared to both sides. Now on the left side, this of course we know is going to factor to become x plus b over 2a squared. And on the right side, we had negative c over a plus b squared over 4a squared. Now those two fractions on the right can have a common denominator if we multiply the left fraction top and bottom by 4a. What that means is x plus b over 2a squared equals minus 4ac or ca plus b squared over our common denominator of 4a squared. Now let's take the square root of both sides. If we take the square root of the left side and the square root of the right side, we'll have to have plus or minus the square root on the right side, and we get x plus b over 2a equals, now we don't know what the square root of the top is. That's plus or minus the square root. I'm going to put the b squared, the positive term, first, minus 4ac. But we do know what the square root of this denominator is. That's going to be 2a. Now, let's subtract b over 2a from both sides. And we have x equals negative b over 2a plus or minus the square root of b squared minus 4ac all over 2a. But we have a common denominator there. We can put those together. And what we find out is that no matter what a, b, and c are, a and b and c can be any real numbers, x will always be equal to negative b plus or minus the square root of b squared minus 4ac all over 2a. And you might remember that from some algebra you've had before, depending on what algebra you've had to be here, but that is the quadratic formula. Now there's not too much that you need to memorize in this class. I really try and help you to learn processes, but the quadratic formula, you need to know that. You will use that frequently in this class. It shows up in lots of higher mathematics and sciences. So there it is. The quadratic formula can always be found as long as you can identify what the a, b, and c coefficients are in a quadratic. So let's use this. We have a little quadratic here, 6x squared plus 3 equals 8x. We could shift that 8x to the left and solve by factoring. We could even divide by 6 and complete the square. But we can do this by using the quadratic formula. We have three methods for solving quadratics. Now here we go. If we take a look at these coefficients, we first have to get it in the form ax squared plus bx plus c equals 0. So let's subtract those 8x from both sides. And this becomes 6x squared minus 8x plus 3 equals 0. And then we can conclude that our a value here is 6. Our b value is negative 8. And our c value is 3. Then we can apply the quadratic formula and say that our values of x that make that equation true, our solutions will be negative b, be careful of your signs here, negative minus 8, plus or minus the square root of our b value, which is negative 8 squared, minus 4 times our a value, which is 6, times our c value, which is 3, all over 2 times our a value, which is 2 times 6. Now if we simplify that, we get x equals negative negative 8, that's positive 8, plus or minus the square root of 64 minus 72 all over 2 times our a value of 6, that's going to be 12. Now, we can reduce that a little bit more. This means that x is 8 plus or minus the square root of negative 8 over 12. But that's an imaginary solution, and we can simplify it a little bit. There's a perfect square of 4 inside there. That factors out, and this becomes 8 plus or minus 2 times the square root of 2i all over 12. And since it's imaginary, we can write that in a plus bi4. I'm going to use this space up here. 8 over 12 reduces to 2/3. That's the real part of our number right here. Plus or minus the imaginary part of our number, which is right there, and that reduces to square root of 2 over 6i. And there's our two solutions to this quadratic. They're imaginary. One of the advantages of the quadratic formula is it works every time, whether the quadratic factors or not, and it finds all the solutions, whether they're real or imaginary like this. Now, the quadratic formula works every time, but you can save yourself a lot of work. Let's take a look at a couple of examples here. We're not going to use the quadratic formula to solve these, but I want to make sure that you note something. If you were to solve this top equation using the quadratic formula, take a minute and look. What would your values of a, b, and c be here? Well, your coefficients, a is 1. The b value would be 4/5, and the c value would be negative 1/3. That'd be a bummer to plug into the quadratic formula, because all those fractions would have to go into their respective places, and we'd have a big mess. We could do it, but they'd be a big fractional mess. So instead, what we do is we can multiply everything on each side of the equation to eliminate those fractions. So take a look at your equation here. What should we multiply both sides by to wipe out the fractions in that top equation? We'll multiply the left side and the right side all by the common denominator, and that is 15. So if we multiply that by 15 and this by 15, it's going to still be the same equation, but it's going to look different. It's going to become 15x squared plus 15 times 4/5 is 12, and 15 times negative 1/3 is negative 5 equals 0. That's a much easier form to use. Here, our a value would be 15, our b value is 12, and our c value is negative 5. That's much, much easier to plug into the quadratic formula because there's no fractions. Take a look at our second equation here. 20x squared minus 60x minus 40. Note here that your coefficients are kind of big. If we used it just as it is, we would say that a is equal to 20, b is equal to negative 60, and c would be equal to negative 40. We could do that, but we're going to get really, really big numbers when we plug everything into the quadratic formula. So instead of doing that, let's divide everything by a constant to reduce the size of these numbers. What can we divide everything by? You might notice we could divide everything by 20. There's a common factor of 20, and if we do that, we get 20 over 20, that'd be x squared, minus 60 over 20 is 3x, and 40 over 20 is minus 2 equals 0 over 20, which is 0. That's again a much, much happier quadratic to solve. Here, a would be equal to 1, b would be equal to negative 3, and c is equal to negative 2. Much easier to plug into the quadratic formula. Now take a look at the bottom one. I'm going to give you a minute just to look at this. You could plug those decimals into the quadratic formula. It'd be a giant calculator mess. what can you do to this equation, like we did to these first two through here, to make the coefficients easier to work with? What can we multiply by that would wipe out all those decimals? Well, we would love it if we could move all those decimals 2 to the right. So let's multiply everything on the left side by 100. We can do that as long as we multiply the right side by 100. So instead of having a equal to 0.03 and a b value of negative 0.04 and a c value of negative 0.1, yeah, again, we could do that, but that's messy. Instead, if we multiply the left side by 100, we would have 3x squared minus 4x minus 10. Much easier coefficients to work with. Here, a would be 3, b would be negative 4, and c would be negative 10. Again, very easy to plug into the quadratic formula. I trust that you could plug those in. I'm not going to have more examples of that. But know that that's an algebraic trick that we can use to make our work easier. All right. Now that we're familiar with the quadratic formula, we want to pay attention to a part of the quadratic formula inside the root within the quadratic formula. Remember what that's called? What the inside of a root is called? That is your discriminant. The discriminant sort of tells you about the nature of the equation that you're trying to solve. Without plugging in all the values into the quadratic formula, sometimes it's useful just to calculate the value of the discriminant. We know that when we go to take the quadratic formula, negative b plus or minus the square root of b squared minus 4ac over 2a, we know that that's the number that tells us whether or not we have real solutions. In order to get real solutions, that number has to be positive. Then we can take the square root. If it's positive, then we're going to get 2 real solutions. If that number happens to be a perfect square, you'll get 2 rational solutions. That is to say, our 2 answers are going to be fractions. That is to say, our solutions are going to turn out to be fractions. If it's a positive number but not a perfect square, that means you would need your calculator to solve it if you wanted to find the decimal approximation, and we'll get 2 solutions, but they will be irrational. That is to say, they will not be fractions. We'll see examples of both of those in just a minute. It's also possible that when you go to calculate the discriminant, b squared minus 4ac, it could turn out to be 0. When the discriminant turns out to be 0, our value of x turns out to be negative b plus or minus 0 over 2a. And plus or minus 0 just disappears. So we would only get negative b over 2a. That would be our 1 solution. So when the discriminant turns out to be 0, we only get 1 repeated rational solution. That is to say, we get 1 answer, and it turns out to be a fraction. And of course, the third thing that could happen is it could turn out to be negative. And I think you'd agree that if this value turns out to be a negative root, then our answer is going to involve I. And that is to say, we'll have 2 distinct imaginary solutions. And by the way, those 2 numbers happen to be complex conjugates, and we saw that in our example that we used for review at the beginning of this lesson. So let's take a look at a couple of examples here. Let's determine the number and type of solutions in each equation. Note, we're not going to solve. We only want to determine the number of solutions and what type they are. That is to say, we are going to use the discriminant b squared minus 4ac. So first of all, we need to rearrange to get this in standard form. 5x squared plus 7x minus 1 is equal to 0. Once it's written like that, we can conclude that a is 5, B is 7, and C is -1. Now let's find the discriminant. B squared minus 4AC is 7 squared minus 4 times 5 times -1. That is to say 49 plus 20, which is 69. Since our discriminant turns out to be 69, that turns out to be a positive value, but it's not a perfect square. So this is the situation we have here. And since it's not a perfect square, then if we go and continue to actually solve that, we would get two irrational solutions. Let's just verify that that's the case. We know that's true because look, if we continued with the quadratic formula, we would say that x is equal to -b, which is -7, plus or minus the square root of b squared minus 4ac, that's 69, over 2 times our a value, which would be 10. Well, sure enough, those are definitely two irrational solutions. We have plus or minus and root 69, that is irrational. Okay, what about the one on the right? What kind of solutions do we have here? It's pretty clear that our a value is 3, our b value is 5, and our c value is 2, and therefore b squared minus 4ac turns out to be 5 squared minus 4 times 3 times 2, or in other words, 25 minus 24. Here our discriminant turns out to be 1. So again, we got a positive number, but this time that is a perfect square. That is 1 squared. So this time we got a positive number, but it is a perfect square, which means when we went and solved this one, we would get two rational solutions. Our answer would be both fractions. Okay, I want you to do these two. Take a minute, pause the video, rearrange these to figure out what your a, b, and c values are, and then find the discriminant and determine which case you have. Unpause the video and we'll work through both of these. Okay, the one on the left, let's shift everything to the left side. 2x squared minus 8x plus 8 is equal to 0. So if we use our discriminant here, our a value is 2, our b value is -8, and our c value is 8. Then b squared minus 4ac turns out to be -8 squared minus 4 times 2 times 8. Or in other words, 64 minus 64, that discriminant turns out to be 0. So what does that mean about this equation? This equation, since the discriminant is 0, is that case right there. There would only be one repeated rational solution to this equation. But you know what? We can verify that. Take a look at this. If we solve this quadratic by factoring, you could factor this into 2 times x squared minus 4x plus 4 equals 0. But that factors again and we get 2 times x minus 2 times x minus 2. Now you tell me, what are the solutions to this equation? They are x equals 2, and the other one is x equals 2. Of course, what did we get? We got the same solution repeated. That's exactly what it said. Because our discriminant was 0, we got one repeated rational solution, and that's exactly what we found. So we didn't need to do this factoring right here. I just wanted to show you that we get exactly what the discriminant says we should get. Okay, and our last one over here, x squared plus x plus 1. I think it's pretty clear that in this equation, a equals 1, b equals 1, and c is equal to 1, and therefore b squared minus 4ac is equal to 1 squared minus 4 times 1 times 1. That is to say 1 minus 4. Our discriminant value here is -3. So if we try and solve this, no matter how we solve it, we would find that because of the negative discriminant, we are going to get two different imaginary solutions when we try and solve. We could complete the square, or we could have used the quadratic formula, but we're going to get two distinct imaginary solutions. Okay, as we kind of summarize what we've done here now, I've got three quadratic equations on your screen. But look one at each of these three, and if you had your choice of solving, how would you solve it? Your primary methods of solving here are the three methods that we've used so far. We can use factoring. We've been using that all semester. We could complete the square. That is to say, use square roots. Or we could use the quadratic formula. Pause the video, make your decision, and then resume and we'll discuss. Okay, well, our top one, the decimals that are present here make that a pretty tough one to solve by factoring. It's also going to be pretty tough to do by completing the square. We could very quickly say that A is 4.5, B is 2.7, and C is negative 1.3. Or we could multiply by 10 to get rid of those decimals. We would probably use the quadratic formula here, because x is negative b plus or minus the square root of b squared minus 4ac. You could plug those values in and you could figure out what the solutions are. I want to clarify a little language here. This thing right here, this is the quadratic formula. We use the formula to solve this thing over here, which is a quadratic equation. A lot of people use quadratic equation and quadratic formula interchangeably. They're not the same thing. We use the quadratic formula to solve a quadratic equation. Okay, our second one, n squared minus 7n minus 30 equals 0. Would you factor, complete the square, or use the quadratic formula? Well, you could use the quadratic formula, but notice that this factors really easily. We know that it's going to factor into n and n because the leading coefficient is 1. And we can factor it into n minus 10 and n minus 7. And n plus 3 equals 0, and therefore n is equal to 10 and n equals negative 3. Factoring is fastest if you spot the factorization. And so this one you would probably solve by factoring. Now our last one, 85 equals x plus 4 squared. Since this thing is squared, we could take the square root right off the bat on that, and we could say plus or minus the square root of 85 is equal to x plus 4. Subtract 4 from both sides, and just like that we've got our solution. We could say x equals negative 4 plus or minus the square root of 85, and boom, we're done. This is a case where we would probably use the square root or completing the square to solve. It was very, very quick and easy to solve. Okay, we're going to wrap up this lesson with one more skill that you need to develop while we're working through this topic. Take a look at this equation, x to the 6 plus 3x to the third minus 40 equals 0. Notice here that that sixth power means that this is not a quadratic, but it sure does look like it, doesn't it? It looks really, really close to the form ax squared plus bx plus c equals 0. So what we can do is we can make a substitution that will make this act like it's a quadratic. Here's the key. When you write the term in standard form, that is to say descending power, look at that middle term. That sort of tells you what our substitution is going to be here. Here's what we're going to do. We're going to let u be x to the third. Because if we write this, this first term becomes x to the third squared, or in other words, u squared. Our middle term becomes plus 3x cubed, which is plus 3u. And our constant term doesn't change at all. We have minus 40 equals 0. Now, that's a pretty easy quadratic to solve. In fact, this one solves nicely by factoring, and we can say that u plus 8 times u minus 5 equals 0. Taking that a step further, we can say that u equals negative 8 or u equals 5. Now we're not done because remember, u was just a nickname that we made up. It was a substitution for x to the third. So we can say then that x to the third equals negative 8 and x to the third equals 5. So solving this, x must be the cube root of negative 8, or x is equal to the cube root of 5. And those are our two solutions. So even though this was a 6th degree polynomial, which we have not handled, we can make it act like a quadratic, solve it, and then complete our substitution. Let's look at a couple more cases. Here's four just very messy equations. These are not quadratics, but they act like quadratics. Let's identify what the best substitution to use for each of these would be, and then we'll actually solve the last two. Let's take a look at the one in the top left here. The focus is on the middle term. That sort of tells you what your substitution should be. The square root of n, let's let that be our value for u. U is the square root of n. Then this becomes 3 times the square root of n squared, or in other words, 3u squared, minus 24 times the square root of n, or 24u, plus 14 is equal to 0. Now we could solve that quadratic, solve for u, and then like we did in the last example, we could back substitute to solve for n. The one on the bottom left, if we rearrange this, we'd put our highest power first, so x to the 2/5 plus x to the 1/5 minus 6 equals 0. So here again, your middle term is sort of your clue. That tells you what your substitution should be. We're going to let u be equal to x to the 1/5 power. Then our first term back here becomes u squared plus that x to the 1/5 becomes plus u, and we have minus 6 equals 0. We can solve that by factoring pretty easily. We get u plus 3 times u minus 2 equals 0. That means that our values for u are equal to negative 3 or 2. Now we're not done because u is equal to x to the 1/5, so we would say x to the 1/5 equals negative 3. Or in other words, that 1/5 power, as you remember, is equal to the 5th root of x. Now we'll raise both sides to the 5th power to cancel out that root. And one of our solutions is x equals negative 3 to the 5th power, which is negative 243. When u is equal to 2, that's the same as saying x to the 1/5 equals 2, which is again the same as the 5th root of x equals 2. We'll raise both sides there to the 5th power to get rid of that 5th root, and we can conclude that x is equal to 32. There's our two solutions. It wasn't a quadratic, but we made it act like a quadratic, and then we completed a substitution to find our values. Okay, up to the top right. What should we let u be here? Well, again, focus on your middle term. That tells you your substitution. Here we should let u be 1 minus p over 2. If we did that, we would have 8u squared minus 14u minus 15 equals 0, and that's a quadratic we could solve. We won't do that one now, but we could solve that one. And let's move on to the one in the bottom right. What should our substitution be? Well, again, your middle term tips you off. We're going to let u be equal to c to the negative 1. That means this equation becomes 28u squared minus 3u minus 1 equals 0. Let's use the quadratic formula to solve that. X equals negative b, our b value is negative 3, plus or minus the square root of our b value squared minus 4 times our a value, which is 28, times our c value, which is negative 1, all over 2 times our a value of 28. But if we simplify that, we get 3 plus or minus the square root of 121 over 56. I made a mistake here. I said back a minute ago that we were solving for x. We're not solving for x, we're solving for u. That's no big deal, but we're solving for u, not x. And if we go a pinch further, we get u equals 3 plus or minus 11 over 56. And so u is equal to 14 over 56, which is 1/4, or u is equal to negative 8 over 56, which is negative 1/7. But we're not done. Remember, we weren't trying to solve for u, we were trying to solve for c, and u is equal to c to the negative 1 power. Now, hopefully at this point in the semester you know that c to the negative 1 power is the same as saying u equals 1 over c. And so when u is equal to 1/4, we can say that 1/4 equals 1 over c, and apparently c is 4. There's one solution. And for our other solution, when u is equal to negative 1/7, we get 1 over negative 1/7 equals 1 over c, and apparently here c equals negative 7. And there's our other solution. So in short, this technique of substitution lets us solve all kinds of really complicated, messy-looking equations beyond what we could normally do by making them look as if they're quadratic. And then we can use factoring, like we did for this one, or the quadratic formula, like we did for this one, to solve. Okay, let's finish this up by doing a work problem like those we did earlier in this semester. When a father in a car and his son on a bicycle work together to give out the morning newspapers, it takes them 35 minutes. If they work alone, it takes the son 25 minutes longer than it would take the father since he's on a bike. Let's figure out to the nearest minute how long it would take the son to do the job on his own. Now, we did problems like this in chapter 7, and so the setup will be familiar even though it's been a few weeks. Let's go ahead and do this. Remember, we solved these using a table. You might remember that we have a row on each table for each participant in this scenario. In this case, we have a father and we have a son. And then for each one of the participants, we know that their work done, that's one column, that's going to be equal to the rate of work times the time that they spend working, and those are the other two columns on our table. So let's look at the scenario. What do we know? Remember, our time worked is the time worked together. And we know that in this case. Together it takes them 35 minutes, so we can fill that value in for both. Now we don't know anything about the rate for either one. But you might remember the example we used then, that the rate of work is simply 1 over the time to do the job alone. And the example I gave back then was, if it takes you 3 hours to drive to Milwaukee, then your rate of speed is you get 1/3 of the way per hour. Now we don't know the time for each individual person, but we do know this. We want to know how long it takes the sun to do the job on his own. Let's call that the time t. That's what we're looking for. Then the sun's rate of work will be 1/t. We also know that it takes the son 25 minutes longer than it would take the father to do the job. So the father takes 25 minutes less to do the job. And we can say that the father's rate is 1/t minus 25, since he needs 25 minutes less than the son does. Now we can use multiplication, the fact that the rate times time gives us our work done. So if we multiply the time of the father times the rate of the father, we get 35 times 1/t minus 25. And for the son, we'll have 35 times 1/t. And the key to this problem is the fact that the amount of work done has to equal one whole job. So we can say 35 times 1/t minus 25, that's a subtraction sign, plus 35 times 1/t, that should equal 1. Now, we can multiply in those 35s to make this equation a little bit easier to work with, and that becomes 35 times t minus 25 plus 35/t equals 1. Now this gives us a rational equation. There's a lot of skills that we've done in this class all wrapped up into one problem. How do we solve this rational equation? Well, remember, we multiply by the LCD, and our LCD here is t times t minus 25. So since this is an equation, we're going to use the LCD to wipe those out. So we're going to have t times t minus 25, that's a minus sign again, times 35/t minus 25 plus t times t minus 25 times 35/t equals t times t minus 25 times 1. I barely fit it on the screen there. That's going to do all of our canceling. So in our first term, the t minus 25's cancel, the middle term, our t's cancel, and in the last term, the right side, nothing cancels. So we have a new equation. We have 35t plus, distribute that in, 35t minus 35 times 25 is 875 equals, and on the right side we have t squared minus 25t. Or in other words, 70t minus 875 equals t squared minus 25t. Well, there's a quadratic that we need to solve. Let's use this space to solve that quadratic. 70t minus 875 equals t squared minus 25t. Well, we'll leave the t squared positive and shift everything to the right side. This is a great place to use the quadratic formula. A equals 1, B equals negative 95, and C equals 875. So we're solving for t this time, so t will be equal to negative b plus or minus the square root of b squared minus 4ac all over 2a, and in this case that becomes negative 95 plus or minus the square root of negative 95 squared minus 4 times 1 times 875 all over 2 times 1. And you can type that into your calculator. Be careful, you're going to get two solutions here. One of them is positive and one of them is negative. The negative one, of course, doesn't make any sense. But the positive one that you should get is you should get a t-value of 84.67 minutes. Or in other words, it takes the sun about 85 minutes to do the job on his own. And we've solved the problem. So we had a rational equation in there, we cleared fractions, we had a common denominator, we got a quadratic, we used the quadratic formula to solve. A lot of concepts from our last 10 weeks all tied into one there. Okay, I'm not going to give you a practice problem like that one, but there will be some similar stuff in WebAssign.